Hello friends, this video on Thermodynamics part 16 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 15. The important topic in thermodynamics, heat capacity. What is heat capacity? Why do we need heat capacity? Before we define heat capacity, let me talk why do we need heat capacity. Do you know what we have learned is the change in internal energy of the system? That is Q plus W. Heat flows, we told that delta U, change in internal energy, is Q plus W. Q is the heat flow. So when you are giving heat to a system, we want to know how much heat we have given, how to find the heat we have given, right? How do we measure the transferred heat to a system? We have given some heat, how do we measure and how much heat has been transferred, whether 10, 30, 40, we don't know how to measure. We need some, volume we can measure, right? Easily just, we have measuring class to measure. Temperature also we can measure. But heat is not temperature. Heat is heat flow. Heat is heat flow. How do we measure heat flow? Correct? Hope you understand this. Heat flow or heat is not temperature. Temperature is different which we measure from thermometer. Heat flow is something different. So the question is, how should we measure heat flow? So experimentally they have seen that heat flow or heat transferred is directly proportional to the change in temperature. Let's suppose the flask was initially at 10 degrees Celsius initially, and we heated this with a small fire, it became 20 degrees Celsius. The same, we had two flasks like that, and the other flask, this flask 1, this is flask 2, was heated with a bigger fire and becomes 40 degrees Celsius. So it is observed that this is what heat we are sending or heat we are transferring, which we can't measure now, but we will try to find a way to measure. But we saw that the heat transferred is directly proportional to the temperature difference, right? This Q is directly proportional to the delta T. That is something which we know by experiment, right? The heat transferred is directly proportional to the temperature difference given both the flasks are same, properties same, mass is same, everything is same, similar. Two similar flasks, the temperature difference is directly proportional to the heat transfer. The more heat you transfer, the more is the temperature difference. The less heat you transfer, the less is the temperature difference. Initial was 10, so here delta T was 10 and here delta T is 30, assuming initial is 10. So if you see delta T is more here. It is also observed that the coefficient depends on size, composition and nature of the system. So for same delta T, let's suppose I'm just telling that if you have smaller flask and if you have bigger flask in giving same heat, this will have less increase in temperature. This will have more increase in temperature. So assuming you start with 10 degrees Celsius, this may end up having 15 degrees Celsius, sorry, let's suppose 45 degrees Celsius, and this may end up having 15 degrees Celsius. So here delta T will be 5 degrees Celsius and here delta T will be 35 degrees Celsius. Just some figures I am throwing. So that means these coefficient is something which depends on the composition and nature of the system. See, first thing we saw that the heat transfer is directly proportional to temperature difference, and since it's directly proportional, we have some proportional constant also. And then experimentally they found that this proportional constant is depending of the system nature, right? If it is, you have more bigger system, the smaller system. So there are a lot of parameters on which this coefficient depends. So as I told, it is found experimentally that this coefficient C is directly proportional to the amount of substance. And there is a new term called molar heat capacity that was introduced. That is nothing but heat capacity for 1 mole. Since we have seen that this value heat capacity is depending on the quantity, its extensive property. So Example, temperature is intensive. It doesn't matter on the quantity. So we don't have something called molar temperature. We don't have, right? You take the any sample from the system, it will be having same temperature. But since this heat capacity is dependent on the amount of substance in the system, or it is an extensive property, we have something called molar heat capacity. That is nothing but the heat capacity of one molar substance. So that is nothing but the heat capacity by total number of moles. That gives you the molar heat capacity. Such kind of thing where it depends on the total number of the quantity of system. We generally have something called molar volume, molar heat capacity, and things like that. So here also we have something called molar heat capacity. The value is C by N. Then we have something called specific heat capacity. So till now we have learned heat capacity, then we have learned molar heat capacity, and now we'll learn specific heat capacity. So what is specific heat capacity? So if you see, it is nothing but the heat required to raise temperature of 1 unit mass by 1 degree Celsius or Kelvin. You can take, because delta T is same, it doesn't matter if it is Kelvin or Celsius. So it is 1 unit mass and 1 Kelvin. Just it was defined to make things standardized so that we can have these values put somewhere in tabular fashion, because it's standardized now. Because you talk about delta T is 1 and the mass is 1. And this is small c. This is big C. Specific heat capacity is small c. This is big C. So the formula, we have got 3 formulas now. The first formula is Q. Heat is nothing but specific heat capacity. Since this was for unit mass, so you have to multiply with the number of mass into delta T. Why delta T? Because this was for 1 degree Celsius. And you have to multiply with the number of the change in temperature. Other formula is Q is equal to C into T. The C is nothing but the heat capacity that takes care of everything, and that is this is not standardized. Okay, because the C depends on the number of moles, the system, the properties, there's a lot of things. So there's no specific standard value of this. Or if you want in the molar form, then Q is Cm, this little bit standardized, into number of moles you get heat capacity into delta T. Hope you understand the 3 formulas. The first one is the specific heat capacity, the most general one. So there you have to multiply with the unit mass, delta T, and this is also a little bit used, that is, they use the molar heat capacity into number of moles into delta T. Let's find a relationship between Cp and Cv, that is heat capacity. This is heat capacity at constant pressure and constant volume for an ideal gas. So at a constant volume, the heat capacity is Cv, as I told you, and at constant pressure, the heat capacity is Cp. Right? So if you see, at constant volume we talked about delta U, right? Change in internal energy, and change in internal energy is nothing but QV, heat supply at constant volume. And now we have the formula of the ways to get this measure this heat supply in terms of Cv delta T. This is number Cv delta T, right? Similarly, at constant pressure, we have something called enthalpy change, and then enthalpy change is nothing but heat supply at constant pressure, and that is nothing but Cp delta T. Correct? These things we know. With this, we can prove that Cp minus Cv is equal to R. How can we do that? See, the formula we know that as delta H is equal to delta U plus delta of PV. We don't know whether pressure is changing or volume is changing, right? PV is equal to nRT. And let's assume everything for 1 mole of gas. So this becomes 1. So PV is equal to RT. So this becomes delta U plus delta of RT. So R is constant. So this becomes delta H becomes delta U plus R delta. Okay. So delta H is what? Delta H is Cp delta T. Cp delta T is equal to delta U is what? Cv delta T. Cv delta T plus R delta T. Delta T is common everywhere. So I can say that Cp minus Cv is equal to, and that is what I have. So heat capacity at constant pressure minus heat capacity at constant volume is constant R. This is a good relationship between the heat capacity at constant pressure at constant volume. So please note here is at the change in internal energy is nothing but heat supplied at constant volume. Change in enthalpy is nothing but heat supplied at constant pressure. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.